After studying this module, you shall be able to know about the complexes having same chemical formula but different constitutional arrangement. Learn the types of constitutional isomerism in detail. Identify the number of isomers possible for the given empirical formula. And evaluate the type of isomerism possible for the given empirical formula.
Dear students, today we will discuss about the isomerism in inorganic compounds. We all know about the isomerism in organic compound. I think all of you have been reading about the isomerism in organic compound. But when we discuss about the isomerism in inorganic compound, it is something little unheard of, little unexplored, and today this is what we are going to discuss. So how to discuss about the isomerism? The compounds having identical empirical formula but differ in their physical and chemical properties, such type of molecules are called isomers, and then this phenomena becomes the isomerism. Typically isomerism is of two types, whether for organic compound or for inorganic compound. We can broadly divide into two categories. The first one is constitutional or structural isomerism, and the second one is stereoisomerism. As I said in the beginning that isomerism in organic compound is well known. Now today we will discuss primarily about the isomerism in inorganic compound in general and coordination compounds complexes in particular. So again we can actually divide the isomerism in coordination complexes that can again be divided into two categories. The first one is constitutional or structural isomerism, which is something like when the molecules have the same number and same type of atoms, but they are arranged or they are attached in a different order. These isomerism have different chemical and physical properties, and such an isomerism can be further divided into 7 different categories. I will briefly first mention about the different categories of this type of isomerism. The first one is coordination isomerism. The second one is polymerization isomerism. The third one is ionization isomerism. The fourth one is hydration isomerism. The fifth one is coordination position isomerism. The sixth one is linkage isomerism, and the seventh one and the last one is ligand isomerism. Now what we will do, we will take one of these categories one by one and discuss in detail about these type of isomerism. So let us start our discussion about coordination isomerism. Now how to define coordination isomerism? Coordination isomerism can be defined when different ligand sets in a complex cation or anion, or we can always say the coordination isomerism is the one in which composition of the complex ion varies. So in a coordination isomer, the total ratio of ligand to metal remains the same, but the ligand attached to a specific metal ion changes. Example of a complex series of coordination isomers require at least 2 metal ions and sometimes more. We can take an example. Let us consider a solution which has 2 different types of species. The first one is cobalt 3+ ion, which is surrounded by 6 ammonia molecule, and the second one is chromium 3+ ion, which is surrounded by 6 cyanide ligands. So what actually happens in a solution, we have 2 different types of species, and it can be defined that this is a coordination isomer with a solution containing reversed arrangement of the ligands between 2 metal ions. For example, we started with the cobalt, which was surrounded by 6 ammonia ion, and the chromium, which was surrounded by 6 cyanide ion. Now what will happen, the isomer will have chromium surrounded by 6 ammonia ligand and the cobalt surrounded by 6 cyanide ligand. So this is something, a very simple example. For example, you can take 2 species Ma6 and Mb6. So the first one is like, when the metals are identical, but if you make the metals different, you can have M1A6 and M2B6. Then the isomers will have M1B6 and M2A6, and then you can have a various combination of such type. Now let us discuss, like, this is a type of isomerism, but how we can separate such type of coordination isomers. So coordination isomers can be separated by a phenomena called ion exchange method. In this method, we can actually separate cations and anions easily. The solution of the complex is first passed through the cation exchange resin. So it is a special type of resin in which cationic part of the complex can be exchanged by a cation of the different type. The second process is when you pass through the anion exchange resin. So what will happen, the anionic part of the complex will be replaced by a different anion. So this is the way we can actually separate the complex, both the complexes of this isomer by passing through the cation and anion exchange resins. So this gives you some idea about cation, basically coordination isomerism, and then you can have the visual which will give you better idea about this particular type of isomerism. So in this module, we are going to discuss about isomerism. Now when we talk about isomerism, everybody is aware about isomerism which is present in organic compound, but the isomerism or the understanding of isomerism in inorganic compound is quite limited. Today in this module, we are going to discuss about inorganic isomerism, primarily isomerism which is present in the coordination complexes. So when we talk about isomerism in coordination complexes, there are primarily two types of isomerism. One is structural isomerism and the second one is stereoisomerism. So what is structural isomerism? Structural isomerism is the one in which a metal ion is surrounded by ligands which are identical. It is only the arrangement of the ligands which is present on the metal which decide about the isomerism. Because of the structural isomerism, the two compounds, they differ in their physical as well as chemical properties, and these compounds are now called the isomers, and the phenomena become isomerism. Now we can take one example. For example, a metal ion M is surrounded by 4 different ligands A, B, C, D. So we can talk about several isomers in which what is the orientation of A, B, C and D on a metal ion. In the second compound, that means the second isomer, we can start with B, C, A and D. So you can understand that all these arrangement will give rise to different type of isomers. The other type of isomerism is stereoisomerism. In the stereoisomerism, the type of ligand and the number of ligands are identical. It is only the spatial arrangement of the ligand which differs. For example, if a metal ion has two different type of ligands, for example A and A prime, B and B prime, then it is the arrangement, spatial arrangement of A versus A prime, B versus B prime, which will be different, and you cannot superimpose two of the stereoisomers on top of each other. And this type of phenomena also give rise to different type of physical and chemical properties.
Let us first learn about constitutional isomerism. Constitutional isomers are molecules that have the same number and types of atom which are attached in a different order. These isomers have very different physical and chemical properties. There are numerous forms of constitutional isomerism, and these are hydrate isomerism, ligand isomerism, ionization isomerism, linkage isomerism, polymerization isomerism, and coordination position isomerism. Let us now understand one by one about the different types of isomerisms. The first one is coordination isomerism. This type of isomerism is found in special cases where both the cation and anion part in the compounds are complexes. Now the metal center of both the cation and anion part can act as coordination center. Isomerism arises from a different distribution of ligand between the two metal ions. Thus, the two isomers differ in distribution of ligands between the cation and the anion part of the compound. For example, the exchange of ammonia and cyanide ligands between cobalt-3 of the cationic complex and chromium-3 of the anionic complex form two coordination isomers. Another example of coordination isomerism is where different metal ions and different bidentate ligands are present in the complex. As you can see that the exchange of ethylene diamine and oxalate ligands is taking place between cobalt-3 of the cationic complex and chromium-3 anionic complex to form two coordination isomers. One more example of coordination isomerism is where identical metal ions but different monodentate ligands are there. The example is here. Now exchange of ammonia and nitro ligands is taking place between cobalt 3 of the cationic complex and cobalt 3 anionic complex to form two coordination isomers. Last example of the coordination isomerism is where identical metal ions exist in different oxidation state, but the ligands are different. As you can see that platinum is showing oxidation state +4 in the cationic part and +2 in the anionic part of the complex. Now again exchange of ammonia and chlorine ligand form coordination isomers.
So, after understanding the first part of the isomerism, which was coordination isomerism, now we move on to the second type of isomerism, which is polymerization isomerism. So, how to define polymerization isomerism? This can be defined by the isomers which have same empirical formula but different molar masses. For example, their order of aggregation is going to be different. That means we can say that they will have different degrees of aggregation. As an example, I can ask you to write down formula for 4 possible polymerization isomers of empirical formula of something called platinum, 2 amine ligand and 2 chlorine ligand, and which is in bracket it is whole n. That means we have the liberty of changing this n to 1, 2 and 3. So we can keep on doing and so on. So that means what will happen, the first example will have 1 platinum, 2 amine ligand and 2 chloride ligand. The second example will have when n is equal to 2 will have 2 platinum ligand, 4 amine ligand and 4 chloride ligand and so on. So this will give rise to various combination. So when we say n is equal to 1, that is going to be the first isomer. That means 1 platinum, 2 amine ligand and 2 chloride ligand. When we change n is equal to 2, the molecular formula of the complex will be 2 platinum, 4 amine and 4 chloride, and the best possible structure for this complex is going to be platinum, 4 amine ligand, the first bracket close, second bracket we can have platinum and 4 chloride ligand. Similarly, for n is equal to 3, the molecular formula of the complex will be 3 platinum, 6 amine ligand, 6 chloride ligand. For this particular empirical formula or the molecular formula, we can write 2 possible structures which will be isomers to each other. For example, the first one will have in the first bracket platinum surrounded by 4 amine ligand, the bracket close. The second square bracket platinum surrounded by 1 amine ligand, 3 chloride ligand and the bracket close whole twice. And then we can further write the second isomer as the square bracket platinum which is surrounded by 3 amine ligand, chloride, the bracket close, and then we can write the platinum surrounded by 4 chloride ligand. So the 4 possible isomers for the same empirical formula become for n is equal to 1, n is equal to 2, n is equal to 3 and n is equal to 3 respectively. For the first one, platinum, 2 amine ligand, 2 chloride ligand. For n is equal to 2, platinum, 4 amine ligand, bracket close, platinum, 4 chloride ligand. For n is equal to 2, and for n is equal to 3 will have platinum, 4 amine ligand, bracket close, platinum, 1 amine ligand, 3 chloride ligand, whole square. Similarly, for n is equal to 3, we can have platinum, 3 amine ligand, chloride ligand and platinum, 4 chloride ligand. So basically the polymerization isomerism differ how the different monomers are arranged in a single molecule. That means how they differ in the degree of aggregation.
Polymerization isomerism. It is the special case of coordination isomerism. It arises when a series of compounds have the same empirical formula but different molecular masses for the salt. Although It is not the conventional polymerization, which involves the linking together of a single repeating unit. An example of polymerization isomerism is provided by a series of salts in which both the cation and the anion contain cobalt 3 plus having the same empirical formula. The value of N can be greater than or equal to 1. Several compounds of empirical formula cobalt NH33, NO2 3, N, where N can have the values 1, 2, 3 and 4.
Now we move on to the third isomerism, which is ionization isomerism. Now how to define ionization isomerism? This type of isomerism occurs for the complexes having same empirical formula but they give different ions in the solution. Now this is important. Let me reiterate it by explaining that this type of isomerism can be defined for the compounds having same empirical formula but they give different ions in the solution. Now it will be clear if we take an example. Let us take an example of a cobalt compound which is surrounded by 5 amine ligand, 1 chloride ligand and 1 bromide. So this compound is found in two different isomeric forms. The one isomer is in solution gives a white precipitate with after reaction with silver nitrate. On the other hand, the other isomer gives a yellow precipitate with silver nitrate. Now how to understand this particular reaction? So let us go in detail about this particular reaction. So the first isomer, as I have just said that for this compound there are two possible isomers. So the first isomer that gives a white precipitate of silver chloride with silver nitrate in solution confirms the presence of chloride ion. So the structure of the isomer becomes cobalt, which is surrounded by 5 amine and 1 bromide, and the chloride atom is outside the complex sphere. That means it is not coordinated to the chloride atom. So this particular chloride atom will immediately react with silver nitrate to give a white precipitate of silver chloride. So what will happen to the second isomer? Let us also discuss what actually happens when the second isomer was reacted with silver nitrate. I told you that in this case the precipitate was yellow in color, which is nothing but silver bromide precipitate. So what actually happens when this isomer is reacted with silver nitrate, the precipitate is silver bromide, which is yellow in color. So the structure of this isomer will be when the cobalt ion is surrounded by 5 amine ligand and 1 chloride ligand. That means the chloride is now coordinated to the cobalt and the bromide is the anion which is outside the coordination sphere. So what will happen? Now this bromide will react with the silver nitrate to give a yellow precipitate of silver bromide. Now as an exercise, I could ask you to write the balance equation for the aforementioned observations. That means whatever the example which I have discussed, I can ask you to write all these observations in the form of balanced equation. Why don't you try that? I think in the background you will be able to see these reactions. Now let us discuss how we can find out the structure of a complex by making use of participation by some reagent and the weighing the precipitated salt. That means can we use this as a technique to evaluate the structure of an unknown compound? Let us take one question in which we try to understand that if a solution of 2.665 gram of chromium chloride which has 6 associated water molecule is treated with a solution of silver nitrate, we obtain 2.87 gram of silver chloride. So the question is, can we use this information to find out or to deduce the structure of complex? So let us go to the next part and try to see what we can do. So first thing is to find out the molecular weight of the starting material, which is chromium chloride, which has 6 water molecule. So it is very simple. We can take the weight of chromium, which is 52. Then we add 3 chloride atoms, which is every chloride atom is 35.5. That has to be multiplied by 3. Similarly, we also add 6 water molecule, which is going to be 6 into 18. So when you do this process, we get the molecular weight of chromium chloride 6 water as 266.5. Then we can go and see what happens to the precipitate which comes out in the reaction, which is silver chloride. Silver is 108 plus chloride is 35.5. So that will give rise to 143.5, which is the molecular weight of silver chloride. Now we can say that a sample of chromium chloride, which has 6 water molecule, contain n number of 35.5 gram of ionizable chloride ions, where n is number of chloride ions outside the coordination sphere. Okay, so that means if we have to find out how many chloride ions are present in 2.665 gram of chromium chloride 6 water, we can simply say that is going to be an equivalent of chloride ion which is present multiplied by 35.5, which is the weight of a single chloride atom, multiplied by 2.665 gram of the chromium chloride by which we started the reaction, and that has to be divided by the molecular weight of chromium chloride 6 water molecule, which is 266.5. So this is one part of the reaction. Let us go to the second part of the reaction. So The second part of the reaction is 143.5 gram of silver chloride contains how many grams of chloride ion? So that is going to be equivalent to the weight of chloride ion, which is 35.5 grams of chloride ion. That means we can write, we know that we obtain a precipitate of 2.87 gram of silver chloride. So that will contain how many? That will be very simple. Take weight of one chloride atom, which is 35.5, multiplied by weight of silver chloride divided by the compound or the precipitate which we obtained, which is 2.87 gram. So now we have two reactions. The first one you can call it number 1, the second one you can call it number 2, and now it is the time to relate these two parts together. So that will be N multiplied by 35.5 multiplied by 2.665 divided by 266.5. This is one part of the reaction which was relating chromium chloride as a whole. This will be exactly equivalent to amount of silver chloride which was obtained in the reaction, which is 135.5 multiplied by 143.5 divided by the amount of silver chloride which was obtained, which is 2.87 gram. So when you solve this equation, you have to find out what is the amount of N or what is the number of N. And interestingly, this comes out to be from this calculation 1.999, which is equivalent to 2. That means now we are able to write down the actual formula of the complex, which is going to be chromium H2O whole 5, one chloride atom which is present in this complex, which is coordinated, and the one which we obtained is how many chloride ions were actually present outside the coordination sphere, and that's what we calculated, that outside the coordination sphere 2 chloride ions were present. Obviously, we started with this formula with 6 water molecule, so there has to be last water molecule which is present as lattice water molecule. So this is what is going to be the overall finding from this question. And what is important, then we can actually calculate how many chloride ions are present inside the complex and how many chloride ions are present outside the complex. So this is what is the answer.
Ionization isomerism. It is shown by the compounds having the same empirical formula, but they give different ions in the solution. Although they have the same composition, this type of isomerism occurs when the counter ion of the complex is also a potential ligand. For example, pentaamine bromido cobalt 3 sulfate is red-violet in color and in solution gives a precipitate with barium chloride, confirming the presence of sulfate ion, while pentaamine sulfate cobalt 3 bromide is red in color and tests negative for sulfate ion in solution, but instead gives a yellow precipitate of AgBr with silver nitrate.
So now we go to the next type of isomerism, which is number 4, and this isomerism is hydrate isomerism. So this type of isomerism is shown by the complexes in which there is a difference between the number of solvent molecules inside, that means the inner sphere, as well as outside, that means the outer sphere of a coordination complex. Let us take this example of a chromium compound. So this chromium compound has 3 different isomeric forms. One form is green in color, the second form is blue green in color, and the third form is violet in color. What is interesting, all these 3 isomers are interconvertible from one isomeric form to the other isomeric form after certain chemical reaction. So if we start from the green crystals, so the structure of the green crystal is when the chromium ion is surrounded by 4 water molecule and 2 chloride atoms which are coordinated. One chloride atom is outside the coordination sphere and dot 2 water molecule. Dot 2 water molecule means 2 outer sphere water molecule or lattice water molecule. How to obtain this compound? This compound can be obtained from concentrated hydrochloric solution, and this compound comes out to be as green crystals. Now when you dissolve these green crystals in water, we get a different or the second form of the isomeric form, which is bluish green in color. What is the structure of this compound, of these bluish green crystals? In this compound, the chromium ion is surrounded by 5 water molecule, 1 chloride atom, and 2 chloride atoms are outside the coordination sphere. That means these are the complex anions, and dot 1 water molecule. So we can see moving from green crystals or green isomeric form to bluish green isomeric form, the proportion of the chloride atoms as well as the water molecule which are present inside and outside the coordination sphere varies. When we take this second isomeric form, that means this blue green isomeric form, and if we heat, then what actually happens, it changes to the third isomeric form, which is violet in color. And what is the structure of third isomeric form? In this compound, chromium ion is surrounded by 6 water molecule and all 3 chloride atoms are outside the coordination sphere. So now we can actually relate all 3 isomeric form. So in the first isomeric form, there are dot 2 water molecule, that means 2 outer sphere water molecule. In the second isomeric form, there is dot 1 water molecule, that means there is only 1 water molecule outside the coordination sphere. In the last isomeric form, which is violet in color, we do not see any water molecule outside the coordination sphere. That means all the water molecules are coordinated. So this is an interesting example in which the variation in the outer sphere and the inner sphere water molecule can change the color of the compound. As we have just visualized, the first compound is green in color, the second one is blue green in color, and the third compound is violet in color.
In case of solvate or hydrate isomerism, the isomers have the same composition but differ with respect to the number of solvate molecules inside as well as outside the coordination sphere. The best known example of solvate isomerism is chromium chloride, which may contain 4, 5 or 6 coordinated water molecules. For example, tetraaqua dichlorochromium 3 chloride dihydrate, which gives dark green crystals, and these are obtained from HCl solution. When complex 1 is dissolved in water, converts into pentaaqua chlorochromium 3 chloride monohydrate, which is blue green in color. Complex 2 on heating converts to hexaaqua chromium 3 chloride, which is violet in color. These isomers have very different chemical properties, and on reaction with AgNO3 to test for chloride ions would find 1, 2 and 3 chloride ions in the solution respectively.
Now we go to coordination position isomerism. That means in this isomerism, normally this type of isomerism is observed in bridged polynuclear complexes where interchange of ligands takes place between two different metal centers. Now let us take one example and then I can explain what is the importance of coordination position isomer. So let us take an example of a cobalt dimer. So cobalt is in the dimeric form, that means two cobalt ions are bridging by one NH group and by one OH group. Additionally, the cobalt ions are coordinated by certain number of amine ligands. For example, the first cobalt ion is surrounded by 3 amine ligands, ammonia ligand, and the fourth ligand is chloride. The second cobalt ion on the other side of the bridge is again surrounded by 3 ammonia ligand or the amine ligand and 1 chloride ion. Now what actually happens if you take this compound and if you think about the coordination position isomerism, then we can easily visualize when some of the ligand change their position from one isomeric form to the second isomeric form. So the second isomeric form again have the cobalt ion, two of them which are bridged by one NH group and one OH group. That the difference is the first cobalt ion has 4 amine ligand. Both the chloride ligands are now coordinated to the second cobalt ion. So the second cobalt ion, while it is bridged by the identical one NH and one OH group, but it is coordinated by 2 amine ligand and 2 chloride ligand. So that means these two compounds which you can see at the background, both these compounds are isomeric in nature, where there is a difference in the position of one or different type of ligands from one isomer to that of second isomer.
Coordination position isomerism. This type of isomerism is observed in bridged polynuclear complexes. Interchange of ligands take place between the two different metal centers. It is similar to coordination isomerism. Notice that a bridged binuclear cobalt 3 complex, as shown here, two different isomers can be generated by the exchange of ammonia and chloride ligands between the two cobalt 3 centers of the complex. Let us try to understand the solution for the example just considered. A. Cobalt NH34 NO22 NO2. In this complex, cobalt 3 NH34 NO22 makes cation part and NO2 come as counter anion, thus makes 2 ions in total. B. In this, cobalt 3 NH35 NO22 makes 1 cation and 2 nitro ligand come as counter anions, thus make 3 ions in total. C. Cobalt 3 NH36 make 1 cation and 3 nitro ligands come as counter anions, thus make 4 ions in total. Here is another solved example. We will determine the formulas for the all possible coordination isomers for the compound cobalt NH36 chromium NO2 6. There are 4 isomers possible by the exchange of NH3 and NO2 ligand displayed here. The compound cobalt NH33 NO2 3 chromium NO2 3 NH33 is also possible. However, plus 3 is the most common oxidation state for chromium and cobalt. So no charges would be present. So therefore no interaction between the two. So they will act as neutral complexes. In this module, we discussed isomerism in coordination complexes in general. Two types of isomerism are possible in coordination complexes: constitutional isomerism and stereoisomerism. Constitutional isomerism is further subdivided into 7 types: coordination isomerism, polymerization isomerism, ionization isomerism, hydrate isomerism, coordination position isomerism, linkage isomerism, and ligand isomerism. Stereoisomerism is further subdivided into 2 types: geometrical isomerism and optical isomerism. Constitutional isomers have very different physical and chemical properties.